in this paper, we've got a question all about the national grid. We've got a little diagram here to help us out, and the first question asks us about transformer X, which is this thing here. Now, if you've revised the national grid, you should know this is called a step-up transformer, and it causes the potential difference or the voltage to increase. Now, at the same time, the current, the rate of flow of charge through the circuit, actually decreases. You don't need to know for this question, but the reason that happens is to reduce heat transferred essentially to the surroundings. But its potential difference goes up, but the current goes down. Now, to be able to work out the resistance of the cable, we need to know our equations. In 2023, the equation sheet was given to you. So it's P equals I squared R, or power equals current squared times resistance. Now on to our first mathematical question of the paper. Now for all of these, I'm going to use the FIFA method. You might know it by different names, but essentially we're going to write down our formula or our equation first, then we're going to figure out what to do with them after that. So I've got power equals current squared times resistance. So for the power, it's in standard form. That's absolutely fine. You can leave it in standard form. If you've got a scientific calculator, that will not be a problem for you in the exam. The current 2000, don't forget to square it, because the equation is to square it, times by R. I'm going to leave R as it is because that's the variable I'm trying to find. So that's your first mark for the equation automatically before we do any sort of fine tuning. So formula, insert values, fine tuning, and answer. Now I've got to get R by itself, so I've got to get rid of this 2000 squared. It currently times by R, so the opposite of timesing by R is to divide it by divide by 2000 squared. You've got to do the same thing to both sides, so we divide both sides by 2000 squared. So therefore we are left with 1.6 times 10 to the power 9 divided by 2000 squared equals R by itself. Okay, so then we put that into our calculator. So you can always do the 2000 squared bit separately if you really want to earlier in the question. That is absolutely fine. But if you do all that, you should get a resistance of 400 ohms. So it's a second mark for that and a third mark for the answer in that question. Got another question next up for part 1.4, which is all to do with efficiency. And again, it's given to us, so we don't need to worry about it too much. It is quite wordy, but don't be lazy. Make sure you get your mark for this question by writing the whole thing out. It says useful energy and total energy input and output. We're going to write this one down. There is another equation involving power, but we're not going to worry about that for now because this question asks us about energy. Next, we're going to write down, same as before, our kind of FIFA strategy and see if we can get a final answer. And I'm not going to write down the equation again just because it's quite wordy. It'll take up loads of room here. But efficiency, it tells us in the question, let's underline our keywords, is 0.992. The useful is what we're trying to find out. Now, instead of writing it out, you can just put an X if you want to. That's absolutely fine. But the total, it tells us, is 34.2. Now, it says gigajoules here. Now, gigajoules, well, normally we'd have to convert it. However, if you look down at the answer sheet down below, the answer actually requests us to give it in gigajoules as well. So normally, you'd have to convert that times 10 to the power 9, but it's already down here, so we don't need to worry about that in this instance. What we do need to worry about though, and that's our first mark, is figuring out what X is. So how to get rid of a divide by 34.2? Well, I've got a times by both sides. So I've now got 34.2 times by 0.992 equals X, the thing I'm trying to find. And if you put those numbers into your calculator, you should find that the answer comes to 33.9, beg your pardon. So X equals 33.9, and it kind of makes sense because it's a little bit less than what it was originally, and it's 0.992% of your original value. In terms of rating this question, I mean, as it's the majority of the marks in this question are to do with equations. Depends how good you are using those. However, I think the rearrangements are relatively straightforward. There's no unit conversions, so I'd say actually this is a relatively easy start to a paper, and there's some basic transformer questions you need to know. Most of these over here, you might have heard teachers say this before, are AO2 questions because you're applying your knowledge, i.e. the equations, to a couple of different situations. Okay, moving over the page to question 2, and we've got a question all about specific heat capacity. Now, this practical is a required practical, which you probably will have done something very similar to this in class. However, there's no 6 marker related to this practical, but it does just kind of come up, and you've got a graph and a question to answer about it. So we've got power supply, a joule meter, iron block, and stop clock. And it says before the power supply was switched on, The thermometer was used to measure the temperature. The student left the thermometer for a few minutes before recording the initial temperature. So this comes up a relatively high amount of times with this practical. It explains why the temperature doesn't increase straight away, and the answer is, why would the person do that? It's so that the thermometer temperature is the same as the block. So essentially, it's about giving the thermometer time to kind of rise to the temperature of the block. You can't just say give the thermometer time to rise, things like that. It's got to be the same as the iron block. That's the whole purpose of leaving it to wait for a little while. Next, we've got a graph on this question here. It tells us the energy transferred between 5 and 10 minutes was 26,000 joules. Tells us the mass of the block as well, and we're supposed to work out the specific heat capacity. And your clue is, and this is in the question for a reason, you've got to use the figure, i.e. the graph, and you've also got to use the physics equation sheet. So I'm going to do the physics equation sheet first. Now luckily there's only one equation that's got specific heat capacity in it, so I'm going to write down here. I'm going to do it in symbol form. It's in words in your equation sheet as well. It's E energy equals mass times by specific heat capacity times by temperature change. I'm just going to write these in here because their symbols are a little bit unusual there. Okay. Now, as you might notice, we have a couple of these things already. So we have the energy. So I'm going to do same as before. I'm going to do my FIFA method to make sure I'm maximizing my marks for this question. Even if I mess up, I can still get marks. So my energy is 26,000, nice and easy. The mass is 2.0. Now, if you look carefully, what we're trying to find is specific heat capacity, C. However, we don't have the temperature change. We have a time. There's no time in this equation, so that's where using the graph comes in. So you might have noticed from the graph, it gives you time on the x-axis and temperature on the y. So what we're going to do, we're going to do it as carefully as we possibly can to make sure we get our full marks this question. It says between 5 and 10 minutes. So we're going to get a ruler and we're going to go from 5 to 10 minutes and see what the temperature change was between those two times. So if we go along, I'm kind of doing this roughly and quickly. Obviously in an exam you'd have a bit more time to be able to do this. But you should be able to spot that the temperature increase goes from about, so that's about 54 to about 28, I'd say. So 54 to 28. So therefore the temperature change, it goes from 28 to 54. So we just subtract those two to find our temperature change. Put that in brackets if you're unsure, just to make sure you don't mess up the calculation. Now the last two steps with this are to just use FIFA, but I've got one marker ready for working out the temperature change, and I've got another mark for putting my values into my equation so far, which is pretty good going. So I'm going to, for my fine-tuning step, just leave this over there on this side. We're trying to get C by itself, so I'm going to divide these two terms over here. So divide by 2.0 and put these in brackets because you don't want to make sure you're dividing in the right order. And now this is 26, so I'm just going to put 26 on this side, save me doing the minusing again, equals my specific heat capacity. So that's my third mark, and my final mark for this question is by putting that into my calculator should give you a specific heat capacity of 500 joules per kilogram per degrees Celsius. Moving over the page to finish off the question, we've got a multiple choice question here. It says tick 2 boxes, and the question says the student repeated the investigation but wrapped insulation around the iron block. What effect will adding insulation have had investigation? So we've got 5 different options here to choose from. Now, wrapping insulation, we should know in this experiment, so that was going to reduce the heat lost to the surroundings or heat transferred out. Now we don't want it to be transferred out. We want all the energy supplied to the block to stay in the block. So therefore it will make the experiment more accurate. That's a good thing for the experiment. Okay. Now it won't affect the output of the heater. It won't affect anything to do with the uncertainties. Won't affect the temperature to rise more slowly. If anything, it'll go more quickly. And the last thing, it'll transfer energy. We just talked about this up here. Reduce heat transferred, but also at a lower rate. It means per second. So it kind of helps it to keep the heat in and reduces the heat transfer out. So for this question as a whole then, how are we going to rate it? I'm going to rate it as a kind of medium because I think you've got an equation in there, but it's relatively tricky with the graph. And the rest of it, it's not the method of the required practical, it's the kind of evaluating it can be a little bit on the tricky side. Okay, over to the right hand side for question 3. We've got a question with a big long parallel circuit, 12-volt battery, and the first question is, it says the 12-volt battery supplies direct potential difference, and asks us to define what that key term is. What is meant by direct potential difference? Now, I know a lot of people in this question in the real exam, instead of talking about direct potential difference, they talked about direct current, because that's commonly taught and is a lot more well known. However, you don't get marks for talking about direct current in this question. The idea is the same, but it's not current. So what you have is you have potential difference, and the two types are direct, which means it doesn't change direction or polarity, and you have alternating, which does this. Okay, now we're talking about the direct current here. So direct current, what you'd say is it doesn't, so PD, you should say, sorry, doesn't change, you could say polarity, or you could say direction. If you're happier using that, that would have got you marks on the exam. Okay, now polarity is a good word to use because it comes up in exam questions and mark schemes. Basically means, is it positive or negative? So as you can see, positive or negative, direct current and direct PD just stay the same throughout. Okay, you can't talk about electrons flowing because that would be current. Right, next bit down, we've got a bit easier, just an equation to look at the equation sheet. In 2023, you've got given that, so it's E n equals charge times by PD. Let's go over the page and we can go about using that equation then. So we've got two mathematical equations here. These are, should be 6 marks if you can use a method like FIFA to work out the correct answer. So we are going to write down our formula first, and then we are going to see how to put our values in. So energy equals charge times by PD. In our equation, we've got 5010 is our energy. We've got charge we're trying to find. Now that symbol we use Q, as I mentioned on the previous page, and the potential difference is 12. So that's your first mark locked in already. Next we're going to figure out any fine tuning. Now how do you get rid of a times by 12? Well, you've got to divide by 12, and that means do the same thing to both sides. So therefore my Q charge equals 5010 divided by 12. So all you need to do lastly is to stick that into your calculator, and you should find that is going to be equal to 417.5 coulombs, and that's your final answer. 3 marks. Next one, we've got another equation. This one would always be in your equation sheet, but definitely was for 2023. It says calculate the specific latent heat of fusion of water. So let's underline what we've got. Now there's only one equation that's got this term in it, so it should be obvious what equation to use. It looks like this. It says E energy equals mass times by latent heat. Okay, so latent heat is the one we might be less familiar with from that equation. We don't need to worry about the temperature. Temperature just indicates its changing state. There's no temperature involved in this equation here at all. So let's put our values in. So same as before, we're going to have a energy of 5010, which is the same as before. We're going to have a mass of 0.015, and latent heat we don't know. So that's our first mark for putting our values in. Next, how do I get rid of a 0.015? Well, I've got to divide by that value to get rid of it from this side, and therefore I've got to do the same on this side to get rid of it as well. Sorry, 15, not 51. So therefore I'm left with latent heat equals 5010 divided by 0.015. If you put that into your calculator, you should find it's quite a big answer, but that's fine. Latent heats are often quite big numbers, and it's 334,000, 334,000. Okay, now that part of the question, I'm going to kind of summarize straight away. Apart from the 3.1, which I think is a little bit tricky because it's not that well taught or learnt, those two should be straightforward. If they're not, you need practice of those, because that should be 6 nice, easy marks. And to finish off question 3, we've got the first of 2 6 markers in this paper, and it is all about changes of state. So it's the electrical circuit was left switched on while the ice changed from a solid to a liquid and increased in temperature to 5 degrees. It says explain the changes in, these are the 2 important words here, arrangement and movement of the particles as the ice melted and the temperature increased to 5 degrees. So there are a couple of things we need to note down before we dive in. It's always a good idea to do a really quick plan of this experiment. So we should know with of this answer, sorry, not experiment, solid to liquid, we should know this is the rough arrangement of particles. We need to talk about both their movement and their arrangement. So between the arrangement, Are they in a regular pattern or not regular? Well, we should know solid is a regular pattern, liquid is an irregular pattern, or it's no pattern at all. Movement, these are vibrating, these particles about fixed points. These are free to move. So that's my really quick brief plan. Keep an eye on what the question is asking me in this 6 marker. The next one we're going to talk about is actually the bit that a lot of people missed out when they did this question in 2023, was then it increases in temperature. Okay, so what would happen then if this increased in temperature? Well, the particles will move about more, have greater kinetic energy. Okay, now I'm going to draft the 6 mark answer now. However, it's really important to note you can use bullet points for questions like this. It's better, easier to mark, and keeps track of your thoughts. Okay, so I've set up my answer here just in those 4 sections. Now you don't need to write all this down to get 6 marks, as with all 6 markers. It's just, is it coherent? But you do have to talk about these 2 things, and also mention about the change in temperature once it's a liquid. So we're going to do first of all in a solid. I'm just going to write out in full, so you've got like kind of a word perfect answer. So you'd say something like particles are in a regular pattern. I'm going to talk about their movement as well. So their movement, particles vibrate. They don't stay stationary, they vibrate. What we say about a fixed position just means they vibrate, but they don't actually overall have any movement. In a liquid, particles are in a random arrangement, or are in no regular pattern. What do you say? Random pattern. And the particles move freely. They don't vibrate, but they're able to move wherever they want to, basically past each other and over into other parts of the liquid. Changing from solid to liquid, a couple of things we could note here as well we haven't talked about yet is that when a change of state happens, essentially there's no change to the temperature of the water. So there's no change to temperature. I'll just write down temp here just to save time. So no change in basically the kinetic energy of particles, but there is an increase in potential energy, or PE. Okay, now you don't need to describe what that is, 6 marker. However, it is worth noting potential energy is essentially the arrangement, the spacing between particles. Okay, so that's what happens in a change of state up here. Now lastly, increase in temperature of a liquid. Well, what happens overall at the temperature of a liquid? The idea is that when the temperature increases, there is an increase in kinetic energy or speed of the particles. Okay, and that's our question 3. And now, as a 6 marker, I'd say personally it's probably about medium, because we should all know about states of matter relatively well. However, it wasn't answered very well in the actual exam, and that's because people didn't keep their eye on what's in the question. Okay, over on to question 4, and as we can see here, we've got 2 more mathematical based questions. So let's see what we can dig out from your equation sheet to help us here. So it says in one day 2,500,000 kilograms of water passed through a hydroelectric dam. Tells us the change in gravitational potential energy, tells us gravitational strength, and we're trying to work out the change in vertical height. So we've got 4 things there. The equation we're going to use to be able to spot is that energy is the mass times by G, which is gravitational field strength, times by delta H, or a change in height. Now, for this part of the question, you might be able to spot there is something that's not in its normal units there, and that's this number up here. It's 367, not just joules, but mJ. It's a capital M, so I'm going to write it down here just to make sure I get my mark for it in this question. You need to know all these different prefixes. It's 367.5, and it's mega. So mega is a capital M, means 10 to the power 6 or million joules. So you can write that down somewhere just at the start in case we forget a bit later. Okay, so next let's put our values in. I've got that number I've just mentioned on the left hand side. You can leave it in standard form if you want to, stick in a calculator just as it is. Next we've got the mass, which is 2,500,000, and G is 9.8 if it's on planet Earth, which they will tell you in the question. Okay. And lastly, we just got times by. I'm going to leave this symbol as it is because that's what we're trying to find out. So 1 mark for converting so far, 1 mark for putting our values in. And all we've got to do now is to go about solving this thing. So will be quite a lot of kind of big numbers involved here. So if you do find it helpful, you can always times those numbers together first. If you want to before you use it, that's absolutely fine to do. I'm not going to do that just to save a bit of room. So I've got my energy on this side. How do I get rid of those two numbers to get this by itself? Well, I've got to divide by both of those numbers. Okay, so both 2,500,000 and also 9.8. Now on this side, if I divide by them, you've got to keep it in brackets unless you want to do that calculation first, which is, again is absolutely fine. I'm going to do it on here, keep it in brackets, and that will then equal my change in height. Now, if you put those into a calculator, you'll get an answer of 15 meters. So 15 meters. Now, just to give you a bit of context for this, some questions you can figure out, is that a reasonable answer? It's a hydroelectric dam, which we should know is a reservoir of water kind of going through a dam and down a river. 15 meters sounds about reasonable for that. They're quite big structures, bigger than kind of a 3-4 story building. So that would be about the right answer for that. If it was 0.15, for example, you should know that's too small. Onto the right hand side, and we've got another equation sheet to find. This time we've got a couple of things to do. We've got a unit conversion, and we've got some standard form to give it in as well. So let's find the equation sheet. First of all, there are two versions of this equation. Either is absolutely fine. I'm going to do the energy equals power times by time. You could do power equals energy over time. Either one is absolutely no problem. And again, let's spot those unit conversions first. I've got this is currently kW, which it should normally be W for watts. So therefore, we're going to write down somewhere here that it's 3,000 watts. So we don't get to use it later. A bit more standard form. I've got 2.16 times 10 to the power 7 is my energy on this side. Again, by using FIFA, we're going to make sure we are getting our marks. And power is 3,000, and time I don't know. So I've got 2 marks straight away just for the conversion and putting my numbers in. Now, how to get rid of a 3,000? Well, it's times by the minute, so therefore I've got to divide by 3,000. So currently on this side, I'm going to have 2.16 times 10 to the power 7 divide by 3,000 equals my time. So that's an additional mark in there, and the time ends up being 7,200 seconds, which is your 4th out of the 5 marks. However, in this question, it does ask you to write your answer in standard form, so you should be able to work that one out because it's not the trickiest example in the world. You move the decimal place so that the numbers between 1 and 10, so 1, 2, 3 places, puts it in there. So therefore, you moved it 3 places, so it's 10 to the power 3 is your final answer for that part of the question. Okay, finishing off the equation then with a graph on the next page, and this wasn't very well answered in the actual exam, even though it's easier than you might think. Now, tip when answering exact graph questions, you've got to mention the axes, okay, so you've got to look at them carefully and quote them in your answer. So let's have a look at what the graph's telling us. So the graph's telling us a solar power system is installed in a village in addition to the hydroelectric generator. Explain why this improves, so it's an explain question, not just describing the graph. Why does it improve the reliability of electricity supply to the village? It says use the graph here. So reliability means essentially something is constant or doesn't change. So we're going to keep that in mind when we answer this bit of the question. So let's talk about then our solar powers. Now we should know over the course of the year that solar power, we're going to talk about first, solar power, the power output would be greater in, and you could say, you know, between April and September if you want to. I'm just going to say summer months. And that's when the hydroelectric power output is lowest. Okay, so solar power output would be greater in the summer months, hydroelectric power is lowest. That whole thing is 1 mark, so you do have to then, that's the kind of describing part. Now we're going to go about explaining it. So it asks about reliability, so it underlines that keyword. Reliability means, are things constant, are they roughly the same, or do they change a lot? So the idea is then that if you had that happening, the solar power would kind of look like that. You'd have an overall more constant or less variation in the power supply. Okay, so therefore you'd say at the end, so there's less variation, or it's a more constant overall power supply, or total power output, I should say, because that's what the graph says. Okay, and that's the second part for this question. So overall for that question, the calculation's a little bit trickier because there are a couple of unit conversions to put in there, and the graph question, which you should be able to get at least one mark, ideally 2 for, I'd say overall, it's probably about medium. Alright, over to question 5 then. So we talk about, initially in question 5, some isotopes emit nuclear radiation, gives us the name of two